Okay, so let's do this radioactive half-life and binding energy question. So number one, you have a 160 gram sample, so that's your MI, polonium-218 that has a half-life of, so T1/2 is 3 minutes. How much would remain after 7 minutes? So delta T is 7 minutes. So, oops, better put I in there so you don't think it's meters. So N is equal to delta T over T1/2. So 7 minutes over 3 minutes. I'd be tempted to call this 2 1/3 just so I don't have to round. And then we do MF is equal to MI over 2 to the N. So 160 grams over 2 to the 2 1/3. Okay, so you're going to need your calculator for this one because it's not going to be an easy one in your head. And it ends up being 31.748 grams. Okay, part B, how long will it take to decrease the mass to 8 grams? So now MF is equal to MI over 2 to the N. So this time you're looking for N, so MI over MF. So again, you're starting with 160 grams and you're going down to 8. So 2 to the N will equal 20. And then you might need to use log or ln here, right? So take the log of both sides. So N log 2 equals log 20. So N equals log 20 divided by log 2. And when you do this, you get N to equal 4.322. And of course, I am assuming you know how to do logs and exponents like that. But if not, for Pete's sakes, when you see me tomorrow, tell me so we can go over it. All right, number 2. When a sample of lava solidified, it contained 27.4 milligrams of uranium. So this is going to be my MI. 27.4 milligrams of uranium-238, which has a half-life, so T1/2, of 4.5 times 10 to the 9th, A, which is, it simply means years. It's Latin for annium. If the lava sample was later found to contain, so MF, later found to contain 18.3 milligrams, then how many years have passed? Okay, so you're going to start off with MF is equal to MI over 2 to the N. 2 to the N is equal to MI over MF. So 27.4 milligrams over 18.3 milligrams. 2 to the N is equal to what? Not 1, not 0. 1.497. And again, you would need to take the log of both sides. So N log 2 will equal log of 1.497. Oops, lost the 2. So N is equal to log of 1.497 over log 2. And when you do this, you get 0.5823. So now you go N is equal to T1/2, oops, no. N is equal to delta T over T1/2. Delta T is equal to N times T1/2. So delta T is equal to 0.5823 times that 4.5 times 10 to the 9th years. And when you do this, you get a delta T of 2.62 times 10 to the 9th years, which is pretty long. Okay, so that's 1 and 2, and then we decided we were going to do 5 and 6. So number 5, determine the binding energy in electron volts and joules for an iron 56 nucleus, given that the nuclear mass, so the mass of the nucleus, is equal to 55.9206 U's. And at the bottom of the sheet, I tell you the mass of the proton that I use. was 1.007276. And I say that I used because depending on your source, it can vary. It and the neutron can vary just a little. So 1.008665 use. So on a test or anything, I'll tell you these so that you'll know which ones to use. Okay, so we're looking for binding energy. So first we need to find our mass defect. So mass defect we know is equal to the mass of the nucleus minus the mass total of the protons plus, lost my thing, neutrons. There we go. Okay, so it tells us in the question that it's iron 56. So if it's iron 56, that means there are 26 protons. How do I know that? Because that's its atomic number. And that must be 30 neutrons. Whoops, too bad I can't spell neutrons. Okay, and so we have our 55.9206 U's minus brackets 26 times 1.007276 U's plus 30 times 1.008665 U's. So our mass defect, or your delta M if you want to write it that way, will be 55.9206 U's minus, I think you get 56.449 126, I believe it is, U's. And so when you subtract here, you get negative 0.5285 U's. And the negative means the mass is missing. Okay, but that's not what the question asked. The question asked for binding energy. So we know we can get our binding energy because it's simply our mass defect times our constant 931.48 mega electron volts per U. Somewhere on this desk I have a calculator, maybe. So I often drop the negative here because I know the negative simply means that it's missing mass, and then multiply by 931.48, and you get a binding energy to be 492.28718 mega electron volts. Okay, so that's in a mega electron volts. Then it wants to know what is it in joules. And so to change to joules, you know the conversion factor is 1.062 times 10 to the negative 19 joules per electron volt. Okay, so we take this number, and I'm going to just multiply it by 1 e to the 6 to get my mega there. And now I'm going to multiply it by 1.602 to the negative 19. And you should get, and I'm just checking to see, is it the same thing I have on the page? Look at that, it is. 7.886 times 10 to the negative 11. 7.886 times 10 to the negative 11. And that will be joules. Okay? I'm going to run out of time. Number 6, determine the mass defect. Oh, we only need the mass defect, so we might be okay here. It'd be good if I was on the sheet. So mass defect will equal, tells us beryllium 8, so 8.003104, and it's beryllium. Beryllium has 4 and 4, so 4 times 1.007276 plus 4 times 1.008665. Do the subtracting, you should get a mass defect of whatever I have there, 0.06066, I believe, U's. and I don't ask it for you in